Today we will take a look at Particleworks GUI and we will build our first model, a model of a gearbox, and I will show you what are the steps required for setting up a Particleworks simulation. This is the GUI, so we have several tabs that I will refer to: the Projects tab, the Outline tab, Property, Color Map, Scene, and Keyframe tabs. If you don't have any of them, you can generate them with window and the corresponding element. If you don't have them overlapping, you can also drag like this and in the center release the tab. So up here we have the button to create a new project and actually also the post-processing tools that we will see in the second part of this demo. For now, I just want to create a project. We want to define a nice location and give it a name. The location is better if it's not in the cloud, and it's better if it's on an hard drive that has quite a bit of space, because we will generate some files that can be heavy. So once the project is created, we can see that we have a demo model folder in which basically every model we will import will be also collected. And then in the scene, so we have one scene here that corresponds to a simulation with a specific numerical settings, basically, or boundary condition. If I double click that, I can see panning out that I can open my scene, my simulation. I have the outline here on the left describing the simulation itself. And for every element, I can check the properties tab. This is our best friend because it will let us change the geometrical or boundary condition properties of every input element. Here we will see also the results element and the post-processing elements. I want you to change the camera to ortho such that the visualization is a little bit more easier and appealing. So this is the simulation domain. You can see that we have a gizmo in the center that we can use to modify the domain easily or drag in the domain. If we want to disable the gizmo, we go to Scene, Show Gizmo. So the domain is where the particles will be studied. So once a particle hits one of these boundary, it will disappear. So only particles inside the domain are allowed. So now we want to actually import the geometry. First thing first, we click create a shape, import polygon files, and we just need to go to the specified directory where we have the models. So this is the geometry from Comer Industries, one of our customer. And if you select all of the STL surface files, we can easily import them. We could also drag and drop inside the interface, by the way. The housing, and there are some other elements. There is a shaft in, a shaft out, and two gears. So as you can see, I disabled the visualization of the housing. I can also change the appearance by going to the Properties tab, Appearance of that element. And I can have some alpha such that I see in the inner section. I can also change the color or any other visualization of the element. Now I need to also initialize the fluid. I can do it by clicking Create a Fill. This is a filling plane that basically creates, in the direction of the arrow here, particles everywhere in the domain if we have an enclosing volume. Before pre-processing, however, and before continuing, I would like to extend the domain, because right now the domain is not, let's say, matching the geometry, so the simulation will not run correctly. If I click on the domain, I can do Adjust Domain and hit Enter, and it will automatically adjust to the entirety of the geometry. Actually, we just want to check what is inside the housing, so I will just drag it like that. Now I need to change the direction of the fill creation. So here in the properties I can go to Y lower, and now I have to make sure that the gizmo, or the origin of the film, sorry, the origin of the fill is actually not inside any solid, and it's in the correct location where the fluid should be. Okay, geometrically we are ready. Right now I can hide the domain, I don't need it. I can also hide the fill, and now I activate the fill for the for the physics, either right clicking here and specifying a new fluid, or I can also change and check the physical properties here of the simulation. By hitting plus, I can generate a new fluid and the polygon. The polygon will be just isothermal. I don't need to change anything else. The fluid, we call it oil, and we just change the physical properties according to something that is more related to oil. The surface tension coefficient is lower than 0.072, and the kinematic viscosity and so on is specified. We go to the interactions tab, MPS contact angle. This is the angle that, let's say, describes the wettability of the surface, and it's an experimental value that usually for, let's say, oils, it's in the range of 30 or less degrees. Okay, once I'm there, I hit OK, and I generated my element, my fluid and my solid. Now I select all the input objects, I apply the boundary condition, and I can see now that those are active for visualization or not, active for the physics or not. The same here, now I activate for the physics, this will appear. Even if it's not shown, it will be still active for the physics. Now I will just hide the gizmo because I don't want to drag any element around. And what is missing now is the keyframe definition, so the rotations. In order to see the rotation, I would suggest you to go here, click this button and change the preview interval to 1 millisecond. And now in selecting the gear tree, I can go to keyframes, rotation, and I want to specify an RPM condition in the direction of Z. And the key, I can generate it here by clicking plus, and it's minus 955 RPM. If I hit play, you can see that it's rotating. It's rotating around the 000, however. So to correct for that, I can center the rotation with the barycenter automatically computed by the software. The shaft out is actually a child of the gear tree, so I can apply a parent, and as you can see now, it's inside here and it's rotating with the gear tree. I want to repeat the process of keyframing for the other objects. For gear 4, we have this, okay, so 0, 0, enter, and then minus 516. Okay, it's also rotating around 000, and now in the end, the shaft in, it's also rotating with an RPM in the direction of Z, and in this case the rotation is positive with 1520. Okay, so I define all the rotation and I correctly see them. Now I just need to apply the correct numerics, so I click on this button to check the numerical settings. So I want to change the particle size. This is the size of the discretization of the fluid. I change the length in millimeter and volume in liter, and the gravity is actually in y, negative y, as you can see. I hit next, I go for an explicit solver. The speed of sound will be discussed later, but it's 80 meters per second. It's 4 times the max tangential velocity of the gear. I want to apply a viscosity and a surface tension solver. Those are some basic solver. And I also want to compute Nusselt correlation based HTC on the surfaces. Then I will need to change the initial dt from estimation of the max tangential velocity and a basic formula that we will discuss later. The initial dt is 2e minus 5 for this case, and I want to save every 1 centisecond, so 1e minus 2. And also I want to change the load torque type to time average in order to have forces and torques on all the elements averaged every 0.01 second. Okay, if I hit next, I can check that preprocessing simulation will be run. In case you have a GPU, you can select the GPU, and then if you hit next, this is the preprocess execution and the script that will be run. As you can see, we have a flag to generate the distance function. This is the discretization of the solid STL that we imported. So the particles won't see the discretization of the STL, but rather they will see during the resolution of the algorithm the distance function, so the rediscretization with a specific grid interval of the given STL. Then I hit next. Also, the simulation execution is normal execution. We don't need to change anything, and I can execute. Before doing some advanced adjustment, I want to activate a Courant Limiter. I hit the small button in the corner here. I go to simulation options, Courant Limiter, such that we don't have very high velocity particles, especially due to particles trapped in the meshing area. So this will stabilize our simulation, and the collision distance is best practice to be put at 0.9. So I will explain later on, also during a call with you, why we change those parameters and what that means. Okay, now I can hit run and execute. As you can see, initially we will see the pre-process of our simulation scene. For every STL, so the gear 3 for example, we will generate a distance function, and this distance function will be saved in the scene df folder. Once every distance function is computed, the simulation will start. So as you can see, after some time, the simulation pre-processing was completed, and we have an information of the number of particles that were generated with the fill, and then the simulation will start to run. So if we go back to the scene tab, we can see the particles generated below the fill level. For this demo, we are using a very big particle size, but of course we can improve that. So in the result here we can see that we have the fill particles, and we have number of particles and the particle size as well. Now the simulation is running, and we can see that we have information for every step, and also information about the number of particles for that step, the dt used in the iteration, the remaining time estimated, as well as the time in second per iteration, an average value. At the end here, we have out equal 1, meaning that we just have one output file. We will see that as soon as we start to collect more results, so as soon as we hit 0.01 second, we will also be able to visualize with the player our results. That will be the topic of our second part of the introduction of Particleworks. For now, let's just wait for more results to come.